So the chairman of this seminar is today also the speaker, Vesselin Drensky. So I have the pleasure to announce his talk. The title is Bicommutative Algebras from Commutative Point of View. Please, Professor Drensky.
Okay, I start with some motto by Gauss. You know that mathematics is the queen of science, the number theory is the queen of mathematics. You see that, I think that this is one of the few mathematicians who is in the bill of 10 German marks. And you can see Gauss and some of his achievements here. But if I want to say something similar this way, I'm not a commutative algebraist, but for me personally, ring theory is the queen of algebra and commutative algebra is the queen of ring theory. So, okay, I don't know who is the Koenig, maybe group theory, but several years ago, I gave a talk on varieties of bicommutative algebras, and I start my talk with the claim that bicommutative algebras are not in the very center of the theory of PI algebras. If you think that the center of non-commutative ring theory is consists of Lie and Jordan algebras, again, bicommutative algebras, they are in the periphery, but nevertheless, they have a rich theory which demonstrates the powerful methods of combinatorial non-associative ring theory. And there is a beautiful combinatorics, nice history, and hidden commutative algebra. So the purpose of my talk is to make more transparent the classical commutative algebra hidden there. And I believe that these ideas may be used also to solve other problems. So my comments in that time was a little bit artistic, that maybe all these things are much ado about almost nothing. So you see here the title page of Much Ado About Nothing by Shakespeare, issued in 1600, many years ago. And first I consider fields of any characteristic, and from some moment there will be characteristic 0, and then a pattern any characteristic. So if you have an algebra, right commutative, the brackets say, and you can change the places and the second and the third variables. And similarly, we have a similar identity, but you can change the first and the second variables. And if the algebra is both right commutative and left commutative, this is called bicommutative. So I'm an old-fashioned person, and I prefer to use Gothic letters for the classes. So B is a variety of bicommutative algebras. So this is the class of all algebras satisfying the identities which are of right and left commutativity. And with F, or with F with subindex D, these are the free algebras in the class. In one of the cases, they are degenerate, and the other they are infinitely generated. And you can imagine this in such a way. You have the free non-associative algebra. This is the algebra of polynomials in countable many, non-commuting, and non-associative variables. Then the relatively free algebra, the free bicommutative algebra, this is a factor algebra of the free non-associative algebra, modulo the ideal generated by all these elements here. And one-sided commutative algebras, they appeared a long time ago in a paper by Cayley. By the way, I give references to all these papers which appear there. There is no need to try to collect, to write them now, because after this, the presentation and the talks, they are posted in the homepage of the seminar. You can see them after. So this is the page. This is a page of the paper by Cayley. And also, if you translate this in a modern language, the algebra which he considered, this is the right symmetric Witt algebra. in one variable. So this consists of all derivatives of the polynomial algebra in one variable. And the multiplication is as is given here. So this algebra is left commutative. This is also right symmetric. Right symmetric means that if you have the associator, you can change the places of the second and the third variables. And also Cayley considered the realization of the right symmetric with algebras in terms of rooted trees. This is also a picture from his paper. And now, if you consider one-sided commutative algebras, one important class, this is the algebras Gelfand-Dorfman-Novikov. Sometimes they are called only Novikov algebras. But these algebras were introduced in the 70s and 80s of the previous century by Gelfand and Dorfman. They studied this in Hamiltonian operator in infinite-dimensional mechanics, and Balinskii and Novikov in relations with the equations of hydrodynamics. So Novikov, this is not Novikov from logic, but his son. He's also very famous, of course, everyone knows him. So originally, the Novikov algebras, they are left commutative and right symmetric. These are the papers which they appear, and their translation. And the opposite algebras, they were Gelfand-Dorfman. This is the pair of Israel, Gelfand and Irina Dorfman. These papers are in Russian. They have a translation in English. And Dzhumadil'daev, Ismailov and Tulenbaev, they describe the free bicommutative algebra of countable rank and its main numerical invariants. So they found a basis as a vector space. They computed the Hilbert series, and in characteristic 0, they found the co-character and the codimensional sequences of the varieties bicommutative algebras. These papers, this with open access, you can see this from the homepage of our institute. And they showed such a lemma that the square of the free bicommutative algebra, this is spanned by such products. You have first multiplications from the right, and then you have multiplications from the left, and you can change the positions of all the elements from the left and all the elements from the right. So you can permute them, preserving everything there. So, and they proved that these elements, which I described here, they form a basis of the square of the free bicommutative algebra. Of course, you can treat it as the elements as rooted binary trees. Here you have the multiplication from the right, and here you have multiplication from the left. Here the indices, they increase from the bottom to the top. So, for example, of degree 4, you have 3 possibilities. Either one branch of length 3 and one of length 1, or 2 plus 2, or 1 plus 3. And of course, if you work with d variables only, you can identify these elements with twice d tuples. So here you have the indices. You count how many times the first variable appears, how many times the second, etc., etc. And here this is 2D-dimensional vector with non-negative integers, integer coordinates. Of course, here you have that the sum of the a's is positive and the sum of the base is also positive. And the theorem of Dzhumadil'daev, Ismailov and Tulenbaev, it's that if you consider the following algebra, GD, it has a basis of the variables and these 2D tuples, which we have. And the multiplication rules are that if you have 2 elements from here, you simply add the vectors. If you have a multiplication by x from the left, you have simply you add one in the corresponding place. From the other side you have, and also I should add also here that if you multiply two elements from here, xi and xj, you get something from here and from here. Then the statement is that these two algebras, this constructed algebra and the algebra of the free bicommutative algebra, they are isomorphic. So here you have one more multiplication, xi, xj. I should add also here, yeah. So if you want to calculate the Hilbert series, what is the Hilbert series? If you have a graded vector space, and you consider a formal power series, which is the generating function of the dimension of the homogeneous components. Of course, if you have ZD grading, you can consider the Hilbert series in many variables. This is an easy consequence of the basis which we already have, that the Hilbert series of the free bicommutative algebra is this. If you have the simple grading, and if you have ZD grading, you have this one. This is an easy exercise. So, and also you consider the square of the free bicommutative algebra. This is an associative commutative algebra, which is isomorphic to these two things. So, of course, it's natural to try to involve the power methods of classical commutative algebra, because the commutative algebra is even not hidden here. And it was done in a joint paper with Zhakhayev. He is also here today, several years ago. So the first step, this is translate everything in the language of commutative algebra. So we consider the commutative algebra in two sets of variables, yd and zd. And if you have if you consider monomials, which are of positive degree, both to respect to y and respect to z, and then the algebra which was constructed by Dzhumadil'daev, Ismailov and Tulenbaev, this is of this kind. It basically consists of elements of first degree and elements of and products of y and z's, and the multiplication rule is if you have two x's and multiply, you get y times z. If you multiply from the left by x, you multiply by y. If you multiply from the right, you multiply by z. And if you have two monomials, you simply multiply them in the usual way. So concerning the basis of this algebra, you can make the things easier because this algebra GD, which was constructed, this is bicommutative. It's easy to see this, and it's a homomorphic image of derivative of the free bicommutative algebra. So both algebras are graded, and the homogeneous component, the first one, maps on the homogeneous component of the other one. So these two algebras, you have an equality between the dimensions of the homogeneous components, but you map every of these monomials to the corresponding monomials, depending on y and z. And since the images are linearly independent, the same holds in the pre-image. So this means that the dimensions are the same. So the algebras are the proof of the theorem. And since the square of the algebra is commutative and associative, you can expect that it has many properties typical for commutative algebras. But the first thing is that this is not the same, because this algebra is not Noetherian. Noetherian means that the left ideas and the right ideas are finitely generated. But here you have an easy example which shows that this is not finitely generated. The ideas, then they satisfy the ascending chain condition. In algebra, this is called that they are weakly Noetherian. And of course, the idea of the proof, this is standard. The square of the generates free bicommutative algebra. This becomes a module of the polynomial algebra in Y's and D's. This module is finitely generated by products of degree 2. And since the ideals are modules, a finitely generated module, they are also finitely generated. So this is simply, and also, this is already not trivial, that over a field of any characteristic, every variety of bicommutative algebra is finitely based, so it can be defined by a finite number of identities. So the proof is typical for methods which were applied in the 70s or even before. This is the method of Higman-Cohen. Before was one of the methods to prove the Specht problem for classes of algebras and groups. You have two papers which are based on this. This is the classical paper by Higman, Graham Higman from 1952. So this paper is 70 years old, and a little bit younger paper by Daniel Cohen in 1967. So how the proof goes, simply I want to give some idea. We consider partially ordered sets, which I keep with relations, which is binary relations with standard conditions, reflexivity and antisymmetry, transitivity. And this set is partially well ordered if for any set there is a finite subset that such that every element is above some elements from the subset. So this means that the set doesn't contain infinite descending chains, and it doesn't have infinitely many pairwise incompatible elements. And the Higman lemma is that if you have a partial ordered set, and you consider the set of finite sequences with a specific partial ordering, this sequence is majorated by a subsequence of the other one, then the set of finite sequences is also partially well ordered. So you apply this in a standard way, simply for the power, for the degrees of the variables. And then this set of the monomials in EZ is partially well ordered. And then you use the standard proof as your basis theorem, for example, which gives that these multiplicative semi-groups of all monomials in Y and Z the Specht property now repeats the final steps of the proof of the Hilbert basis theorem. You can see in the paper, this one. But in the case of characteristic 0, when you study polynomial identities, you have it's enough to consider the multilinear polynomials in the symmetric group from the left. This is the standard action. And then the multilinear elements, they become a module of the symmetric group. And in the study of varieties of algebras, you have the codimension sequence. This is the dimension of the multilinear polynomial identities. And also the co-character. The co-character, this is the character of the symmetric group, the component of degree n. And the reducible characters of symmetric groups, they are indexed by partitions. Partitions that are decreasing sequences of non-negative integers with some n, and this is the co-character which you have. So the theorem for of the same paper by Dzhumadil'daev, Ismailov and Tulenbaev, this states that in characteristic 0, the codimensions they are given here. This is 1 for the first one, and then 2 in power n minus 2 for positive things. The exponent, this is the limits of the nth root. This exists and is equal to 2, and the co-character sequence is given in this formula. In particular, it follows from here that the variety of bicommutative algebra is generated by the 2 generated free bicommutative algebra. So the basic rank is 2. But I simply want to mention that we can combine ideas from the original proof with the approach of a paper of mine, which appeared 3 years ago. So we identify the algebra of, which we constructed GD with the free bicommutative algebra, and we work in the algebra of monomials into variables. So if you have such products, then the multilinear element consists of, here you have k is bigger or equal to 1. The number of z is also bigger or equal to 1. Here these are order, here these are order. So obviously, the number of such elements, which are the basis elements, this is such a sum, which gives immediately the formula. The same is for the other one. This is exactly as in the proof. For the co-character sequence, we can proceed in the following way. We consider the action of the general linear group. So it was here. The general linear group, it acts in a canonical way on the vector space with basis x, consists of x's, and you extend this action diagonally on the free bicommutative algebra, and you have a module. This module is with some multiplicities of the reducible GLD modules, and these GLD modules, they are again indexed by partitions, and we have results from the 80s with our Beryl independently, which give that these multiplicities here, they are the same as the multiplicity in the co-character sequence. And this one allows to compute the co-character sequence easily. So if you work with the algebra of G, which we constructed there, the square of the algebra is simply the tensor product of the augmentation ideals of these 2 polynomial algebras. Augmentation ideal, this means that this is the ideal of polynomials without constant terms. So we know that as a module, the augmentation ideal is a sum of the modules which consists of this form. So we have to compute the tensor product. And there is the Young rule. This is a special case of the Littlewood-Richardson rule, which allows to find the product of reducible GLD modules. So this is the following: if m is bigger or equal to n, then you have such a sum. Here, this is a small example. If you have the 6th module and the 3 module, you should add 3 boxes here in such a way that they are only on the first and the second line, and 2 green boxes cannot be in the same column. So this is the result here. And of course, if you use this formula here, it's easy to find the result. Simply you have to count the number of the modules which appear here. Also, I want to mention 2 more results. One of them is that the variety of bicommutative algebra in characteristic 0 is generated by one two-dimensional algebra. This is the multiplication rule of the algebra. And also that this variety of the bicommutative algebras, this is minimal of exponent 2. If you consider a proper subvariety, then the codimension sequence is a polynomial growth, and the exponent, of course, is 1. So this is. Now, I again work over a field of any characteristic. So what is a Grobner basis in the commutative case? So you consider the semigroup of monomials in D variables. And we assume that it is well ordered. And this ordering is compatible with the multiplication. So it's preserved when we multiply two monomials by another monomial. So if you have a polynomial which is non-zero, you take the leading monomial with respect to ordering. And if initial ideal, this is the set of leading monomials. And this is, of course, an ideal of the semigroup of the monomials in D variables. So something is a Grobner basis of the ideal if for every element of the ideal there exists an element from the Grobner basis such that the leading monomial of the polynomial f is divisible by the leading monomial of this fi. Here there are pictures of Bulgarian and his advisor Grobner. So the Grobner bases were introduced by Bulgarian in his PhD thesis, and he named this Grobner basis because he was thankful to his advisor for Grobner. Also, it's easy to see that if you have a monomial ideal of the polynomial algebra, which is generated by the leading monomials of something, or if you use the Dixon lemma, every ideal of the polynomial algebra has a finite Grobner basis. This is some part of the paper by Dixon, and stated that in his paper that applied to monomials. It's difficult to read such papers because they are in a language which is not very close to the modern language. But it's a nice. Bulgarian gave an algorithm which is very easy. So if you have an ideal of the polynomial algebra, and it's generated by some set by the Hilbert basis theorem, you know that every ideal of the polynomial algebra is finitely generated. And if you take two polynomials from this set and you compare the leading monomials, you have two operations between them. If one of the leading monomials divides the other leading monomials, you simply replace the polynomial, this one, with such a polynomial. You simply kill the leading monomial here and replace it with something smaller. And also, if two of the leading monomials, they can be made equal if you multiply them with some monomials. Then again, you add to the Grobner basis, to the basis, this polynomial, and it's known that this process stops in a finite number of steps, and the obtained set is the polynomials, the set of polynomials of the Grobner basis. of course, everyone doing commutative algebra, even non-commutative algebra, knows that Grobner bases, they are used in many computations in commutative algebras and right geometry. And I give simply a simple example. If you consider the factor algebra module of the ideal, as a vector space, it has a basis consisting of all monomials which are not divisible by any leading monomial of the polynomials in the Grobner base. So this is the some statement which is used quite often for different purposes. And of course, also the polynomial algebra. Of course, if you read the history, you can see that the ideas of Buchberger, they appeared also in the work before him, but in particular, his algorithm is in the base of many of the, here, this is DTH, of the computations with polynomials. For example, Hironaka, he had a paper using similar things. Nikolai Günther, he had this even in 1913. Since I don't write this because in that time it was difficult to find an English translation, but here this you have the coordinates in the Jahrbuch. And also he has something which is already in French, much later. So these are pictures of Hironaka and Günther. By the way, the mathematicians know Günther mainly for his results in differential integration of equations, analysis, mathematical physics, hydrodynamics. And maybe this is the reason that the papers in commutative algebras, they were overlooked. But you can find a detailed description of his contributions to algebra in a paper published in German with English translation. So similar investigations, they were done independently in non-commutative algebra. So this is well, this is not this one. Kirchhoff, he developed his own Grobner-Kirchhoff basis. This is the paper by Kirchhoff in 1962. And in the case of associative algebras, it was developed by George Bergman in his diamond lemma. It's amazing that Bergman wrote a paper of 41 pages, appeared in Advances, in a super journal, and it starts, the main result in these papers are trivial. So this is a little bit funny beginning. So, and three Chinese mathematicians, Bai, Chen, and Zhang, they established quite recently that the ideas of the finitely generated free bicommutative algebras, they have finite Grobner basis. And there is, it was really very recent because the paper was posted in July a year ago. And in November, it was published online in multilinear algebra. And this was a demonstration of the powers of the method Kirchhoff for the study of ideas of non-commutative, non-associative algebras. And I simply want to show that their theorem can be obtained as a corollary of corresponding theorem in the commutative case. So we identified the square of the free bicommutative algebra with the ideal of the polynomial algebra into the variables generated by the monomials which depend both on y and z, and to introduce an arbitrary linear ordering. Then the set of the leading monomials consists of a finite number of elements of the first degree, and those which are in the mutation ideal in the square, So since the semi-group of commutative monomials in Y and Z, this is something which is finitely generated commutative, you can apply the Hilbert basis theorem or the Dixon lemma, and you see that this ideal has a finite number of generators. And of course, this implies the theorem because a subset here is ideal if and only if this is stable on multiplication from both sides by the elements of X. And now I go to the Gelfand-Kirov dimension. What is the Gelfand-Kirov dimension? It measures the growth of the algebra. So you take a set of generators. So the algebra is finitely generated. This is an arbitrary algebra. And you consider the growth function. So you take the first degree, the second degree, etc. The 0 degree, this is either the field or 0, depending on the algebra with one or without one. And this growth function, of course, it depends on the set of which generate the algebra. For different V, you can different generating function. But nevertheless, the symptotic behavior is the same. If you take a logarithm, limit superior of this logarithm doesn't depend on just of the generating set, and this is called the Gelfand-Kirov dimension. The Gelfand-Kirov dimension was introduced in 1966. First, it was announced in the Russian doklady, and then the complete text were in French. So, if you have a finitely generated commutative algebra, its Gelfand-Kirov dimension is a non-negative integers. And in the paper by Chen and Zhang, they give a simple combinatorial algorithm to compute the Gelfand-Kirov dimension of polynomial algebra, modular and ideal. The input consists of the leading monomials of the Grobner basis, and the output is the Gelfand-Kirov dimension. So how this algorithm works? They start with a non-empty set of monomials in the axis, and they define, so the set is finite, the minimal n with the property that it divides, that the elements of this set divides in this powers x1, x2, xd in power n. And if you have such a monomial, then you take the s degree to be the number of i's, such that this the corresponding degree of xi is bigger than this integer cs. And if you have an ideal generated by the set S, and you consider the elements which are not in the ideal, so this is the ideal in the semi-group, then the maximum of this numbers SD, S degree, this is the S degree of the set of monomials which are not divisible by the monomials of S. I give a small example. With red here, this is this monomial. With blue is this monomial. So this is the degree of x1, the degree of x2, etc., etc. U is the monomial which is in green. And you can see that this integer, which is the upper degree, this is 6, and you have 3 degrees, 3 variables which are degrees higher than 6. So this degree is 3. And the theorem is that if you have the Grobner basis of a non-trivial idea of the polynomial algebra, and you have the set of leading monomials of the Grobner basis, then the Gelfand-Kirov dimension of the algebra, this is the S degree of the elements which are not divisible by the elements, the leading elements of the leading monomials. So even here, this algorithm is really an algorithm because it's enough to consider only the elements which have degree in each variable, this number C plus 1. So it's enough to check only a finite number of monomials, and it can be done, of course, quite easily. And now the idea of the proof is the following. If you have such a monomial, and this degree is m, this means that only m of the indices here are larger than this number c. So for example, if the first m are larger, then it's easy to see that all monomials depending on the first m variable are not divisible by the leading monomials of the ideal. So this algebra grows not slower than the polynomial algebra, because the polynomial algebra has exactly these monomials. So the Gelfand-Kirov dimension of this algebra is larger or equal to the Gelfand-Kirov dimension of the corresponding polynomial algebra. On the other hand, if you consider such a monomial, you have only m degrees which are bigger than this number. So, roughly speaking, the factor algebra behaves as a finitely generated module of the polynomial algebra in m variables. So you have the opposite inequality. So you have the equality, the equation. And of course, by Chen and Zhang, they proved that using this algorithm, that finitely generated bicommutative algebras, they have an integral Gelfand-Kirov dimension. Again, you can change their proof and to make it from commutative point of view. You simply consider the growth function of the algebra, and you consider linear ordering, first by degree, and then in an arbitrary way. And you consider the leading monomials of the ideal. And S, this is the factor algebra, modulo the monomial ideal, which is here. So it's known that these two algebras, they have the same Gelfand-Kirov dimension because they have the same growth function. So this algebra S is graded, and this homogeneous component is of dimension equal to the number of monomials of degree n, which are not in the monomial ideal. So this is the formula. And of course, you know that this algebra, which consists of the elements of S which are of degree bigger without linear and constant term. This is a module of the polynomial algebra in two sets of variables. And this module is finitely generated. And by the Hilbert-Serre theorem, this is if Hilbert-Serre is a rational function. And this rational function, this is a product of the denominator, it's a product of binomials of special kind. And also, this is known that if you have a Hilbert series of an algebra, which is a rational function with polynomial growth of the coefficients, and it has a pole of order m in one, then the Gelfand-Kirov dimension is equal to this, the multiplicity of this pole here. So this is, for example, you can find a reference in a paper or in a book by Ufnarovsky. And of course, here you get immediately that the bicommutative algebras, they have an integral Gelfand-Kirov dimension. So already this is not a secret that I was a referee of the paper by Chen and Zhang. And I recommended to have three options and to choose one of them. First of all was to revise the paper in the spirit what I present in my talk today. So this is a part of my referee report. And of course, the advantage is here that the paper will be shorter and it will be easier to follow by persons who are not experts in bicommutative algebra. And then the other thing was to leave the text as it was and to add an appendix. And really I was ready to write the appendix if necessary. And the third one was that to leave the things as they are, but someday maybe I'll write a short paper with title close to the title of my talk and to present these things. And of course, in the second and third case, the referee will be no anonymous anymore. And the answer was that it's better to leave me to write a paper someday, and to leave the paper as it was. So finally, I want to say that during my talk, most of the I commented results which are obtained with methods typical for non-associative algebra and how they can be obtained in a natural way to classical methods commutative algebra. So I want to state explicitly that the results are interesting. Their initial proofs are highly non-trivial, but once the results were obtained, it was natural to look at them also from another point of view. So this is simply. In conclusion, I want to say that several times I claimed that in different languages, in singular and some languages in plural, for example, in Bulgarian and Russian, in German, in Italian, in Portuguese, this is mathematics is in singular. But in French and in Spanish, this is in Spanish, for example, this mathematicas or les mathématiques in French. In English, you still keep the plural, but you say mathematics is in singular. So there are two kinds of mathematicians, two kinds. One of them believes that there is one mathematics, and the other means that there are many mathematics, and each person works in his own mathematics or her own mathematics. In the case of algebra, algebra is in singular all the languages. So simply, it's a good idea to have an idea of many parts of algebra, not only the part which is interesting for your own. So I think, thank you. I finish.
Thank you, Professor Drensky. It turns out that referee reports make interesting research and interesting talks. Yeah, so it's my pleasure to ask for comments and questions.
I stop sharing the screen.
Yep. You can keep sharing because somebody may ask you to show you some of the slides. Yeah. So comments and questions, please. By the way, there were some glitches every now and then. I don't know if it was just me who experienced this or it was everybody. I hope the recording will be okay, but the slides were very good, so they'll probably make up for the glitches.
Can I make one comment?
Yeah, sure.
So I am Askar Dzhumadil'daev. So thank you for a very interesting talk. I'd like to make one comment that may be not related to this topic, but as I understand, Professor Bai and two of his colleagues, but I forget their names, they have introduced one interesting notion they call transposed Poisson algebra. If Professor Bai is here, I can ask him, maybe.
This is not the same Bai.
Ah, it's another Bai.
Not the same Bai. Sorry.
Okay. So I have introduced one more class of algebras that I call weak Leibniz algebras. So difference between Leibniz algebras and weak Leibniz algebras is the following. For example, if you consider any Leibniz algebra, they have no any ideal. They are not simple Leibniz algebras. And weak Leibniz algebras has examples of that are simple. And as it turned out, class of weak Leibniz algebras and transposed Poisson algebras are in some sense are the same. This is just one my remark. that is similar to remark of Professor Drensky about new proof of these authors of Chinese mathematicians. So, and by the way, I did talk about weak-lateness algebra exactly in conference that was dedicated to Professor Drensky's anniversary, 70th anniversary. But in the time I was ill by COVID, exactly in that day, and I was not able to mention these results. So thank you. It's end of my comment.
Okay, thank you, Oscar.
So more comments, more questions?
By the way, when I was in Germany, I had a colleague from China, and he claimed that my name is very difficult, but every 10 Chinese is Lin. Yeah. So from Vesselin, I was Mr. Lin. Good. And since Lin means a small forest, and the Chinese character for Lin, this is 2 trees, I was Mr. 2 trees.
Oh. By the way, on the topic of multiple mathematics, I wish computer science was somewhere near that, because there are not only multiple theories in computer science, but also multiple versions of the same theory in different notations. And this makes things a lot more difficult. Life is a lot more difficult. Every paper starts with preliminaries, introducing basic notations, etc., in theoretical computer science. Nothing like algebra, where you can start from the theorem in the first line of your paper, and you know everybody will understand the notation. So, are there more questions, more comments on the talk?
Yeah, yes. I give some comment. Well, we are. Thank you, Professor Drensky. You opened the secret. you are referee of our paper, and you gave some technical proof, a new proof. Today we understand your new proof. So thank you very much. Okay.
Thank you.
Thank you. That you had a nice paper.
So the first proof is never optimal. That's
no, the first proof was optimal, but simply it was from another point of view.
Yeah. More questions, more comments? Okay, if they're none, I will just stop recording, but the meeting